And maybe we start. So we are very happy to have Tracy Northup here from Innsbruck. It's actually quite a coincidence because I visited in September, I visited Jakob in Innsbruck. He lives there now with 90% of the Schmidt-Kahlas that I knew back in the days. Georg was, by the way, my flatmate for what he wanted to do for 4 weeks. And then it lasted, I think, 1.5 years or something like that. So we we arrived in Innsbruck, and then we walked through the inner city, and then we met Tracy. And it's not that we are super familiar, but I was like, and I know you from somewhere. And then Georg introduced us. And the first question I, of course, asked whether she would like to speak at our quantum seminar. So there's that. Thanks for coming. She did her PhD as a group of Jeff Kimball in 2008 on coherent control in cavity QED. I browsed through her thesis and I downloaded it. So I'm checking for typos right now. I will send you my comments later. It's yeah. Back in the days, she was still working with single atoms. I'm not sure whether that is still something that she does, but she has transitioned to Innsbruck in 2008, working on ions, I believe, and has been there ever since, right? And climbing up the career ladder from postdoc, who were university assistant to assistant professor to, I believe now, associate professor. In 2016, I mean, she won a few awards, and maybe one that I can mention is a START Award, which in 2016, which is from the Austrian Society for Science for young researchers to start their own groups. So yeah, without further ado, thanks for coming. We are very happy to have you here.
And thank you so much for the really kind introduction. And I'm really glad that we ran into each other in September in downtown. It's really a pleasure to be here. So I actually haven't worked with single atoms or with neutral atoms. I think that's right, since I came to Innsbruck. And I think at the time, looking at postdoc positions, it was so interesting to me to hear about ions, because it felt like all of these things that I had wanted to be able to do with these atoms, these long storage times and this really precise coherent manipulation, all of a sudden these were easy. And of course there were new problems that came along with the ions, but it's been a lot of fun. So I'm looking forward to telling you about the work that we're doing with trapped ion interfaces. And in particular, if there's kind of one question that I want to focus on in the talk, it's the question of, can we construct future quantum networks from trapped ions or based on trapped ions? And so I've split this into a handful of parts. I want to start out by, of course, addressing the question of why one would want to construct quantum networks. And then let's move on to thinking about how we can understand trapped ions, not only for quantum computing, which many of you are very familiar with, not all of you, but also for quantum interfaces. And the heart of my talk will be focusing on coupling two remote ion traps via optical cavities. And I'm happy to share some recent results that we have from that experiment. I'll tell you about where we're headed and how we'd like to move beyond this link between two nodes. And finally, I want to mention something a little bit different at the end, work that we're doing on hopefully towards preparation of macroscopic quantum states of motion. So it will be still ion traps and also still ions actually, but now adding an additional, and still cavities, but an additional ingredient of nanoparticles. So with that in hand, let's start talking about why we would like to construct quantum networks. And so this is a picture from a consortium that I'm part of as part of the EU quantum flagship called the Quantum Internet Alliance. And it's kind of this vision of a European quantum internet. The idea that we could link together remote sites over long distances, hundreds of kilometers. And when we think about a quantum internet, what we're really imagining is the ability to distribute quantum states. Again, ideally over long distances with high fidelity, and of course, as fast as possible. So why would we want to do that? Why is it an interesting task? I think, here is something I like to come back to is a table that was published in this nice science article by Stephanie Wehner, David Alkus, and Ronald Hansen. And they're considering the different possible stages of a future quantum network. And what I like about this image is that it addresses the fact that a quantum internet or a quantum network isn't going to be one single thing. And so there's not going to be a moment or one moment when you say, okay, now we've created a quantum internet and it can do everything that we want a quantum internet to do. In fact, there's going to be kind of a hierarchy. There are stages actually at the bottom, this kind of first stage, which is the simplest of a trusted repeater stage. This is something that's already a commercialized technology where we have the capability for example, quantum key distribution. Where two parties would be able to establish an encryption key that's provably secure. Then climbing up this ladder of functionality in the diagram, the idea is that with more and more capabilities, we can then do more and more complex protocols and applications. So again, QKD is an example from the first stage of this diagram, and I wanted to show you kind of a couple of other examples. The idea would be if you had then the ability, for example, not only to generate entanglement between remote modes, but also to store it. That's this idea kind of 4 stages up of a quantum memory. You could start to think about protocols such as blind quantum computing. And I think that probably resonates with a lot of us in terms of how we think about, well, how we use our computers and mobile devices today, where locally we may have limited resources. We have some task that we want to send to a remote computer. And then in the future, this is, I want to send my task to a quantum computer. There's only a few of these, they're very powerful, but I don't want the quantum computer or the owners of the quantum computer to know what I'm trying to calculate. And this is something that you could do in this kind of a quantum network protocol for blind computing. And then a final example that I want to mention kind of even further up the chain is if you could really have few qubit fault tolerance. That is, we should consider the situation, what if we already have small quantum computers, but by themselves, they're not yet powerful enough to do something that really surpasses classical capabilities. And in that sense, we could really think about the benefits of networking these devices to build something that only once it's networked together can achieve a quantum advantage. So with those handful of examples, I hope I've kind of given you the sense that quantum networks have a wide variety of applications, and that's going to depend on the functionalities that we have available. And so moving on from that to thinking about what this is going to look like, this is a kind of picture that may be very familiar to some of you, maybe less so to others. It's actually a photograph from Rainer Blatt's experiment here in Innsbruck, sort of looking in at a very prettily lit up ion trap inside of a vacuum chamber, a linear Paul trap. And so I just want to mention the kind of things that one could do now locally with state-of-the-art quantum computers based on ion traps. So one example would be kind of the creation of entangled states of up to 20 ions. And in that case, we're talking about having the capability to do gate operations with high fidelity on individual ions in a string of 20 ions for computation. And you can even talk about sort of going up to say 50 ions in this paper that's from Chris Monroe's group in Maryland, now at Duke. If you are less interested in the ability to do individual addressing and it's sufficient to do collective gate operations, for example, for quantum simulations. So here I'm just trying to point you to some kind of context where people are now doing experiments with tens, 50 ions. And so you could think, well, what keeps us from adding more and more ions to these kind of experiments? And the answer is that the more ions you're adding in, the more time that's required for these gate operations, and the more opportunity you have for crosstalk, which is definitely a bad thing, between these collective motional modes that you rely on for gates. So your fidelities are compromised, things start to take more time. And so people tend to think about possibly, kind of hundreds of ions in a single trap, but nobody's really envisioning that you're going to be doing these computations with much more than that in a single one of these kind of linear traps. So what are the alternatives? Well, from almost 20 years ago now, Dave Wineland's group put forth this proposal for a so-called quantum CCD architecture, about shuttling ions around to different zones of a structured trap in order to address that issue. And you see, actually, you know, so I won't try to explain this paper to you because it's from Mainz. Here's a really beautiful example of a more recent realization of this concept, the idea that you could use shuttling operations to generate entanglement. So there's a lot of work being done in many groups on this kind of approach, the idea of scaling up the number of ions in a computer through shuttling. And that's certainly very promising. But is that going to get us to, you know, thousands of ions? Is it going to get us to millions of ions? I think at some point you have to consider that maybe you're not going to have all of your ions on the same chip in the same device, even if it's a complex device that allows shuttling. And you have to think about then optical links to other devices. So here's an illustration of that concept from a paper by Chris Monroe and Jung-Sung Kim. This is a picture of a chip with trapped ions on it, but you see two interfaces via this fiber A and fiber B that are connecting those ions to similar chips at some distant location. And here they're illustrating these interfaces as being potentially based on cavities. There's another picture that's sort of more explicitly illustrating a cavity-based interface in an article from Nicolas and Sanguard and colleagues also about 10 years ago. So what I've tried to motivate here is that optical interconnects offer a very promising route to scaling up ion traps beyond a single device. And simply from the point of view of building more sophisticated quantum computers, this idea about distributing computation really then seems to call for having optical interconnects as an important component. Are quantum computers the only application here? Certainly not, but I think it can be really a powerful motivation. So I hope I've kind of given you a broader sense for why we'd like to build quantum networks, and in particular in the context of ions and the current state of the art for quantum computing, that in the longer term, as we're able to do more and more on a single chip, it also becomes more and more interesting to connect together distributed devices. So with that, I want to turn to the second part of my talk and consider these trapped ions as quantum interfaces. And so I've shown you this picture already, and I want to just kind of highlight for you, in particular for those of you who aren't working with trapped ions, the kind of things you should keep in mind that one can do with these systems. So I, of course, then encourage you to get more details from your colleagues in Ferdinand Schmidt-Kahler's group. But the thing you should have in mind for this talk is in particular so-called linear Paul trap, where applying radio frequency voltages to the electrodes of this trap confines ions in a pseudo potential in 2 dimensions, and along the 3rd dimension, this DC voltages provide some confinement. So here I'm going to tell you about experiments with these linear Paul traps that are kind of macroscopic things that you could hold in your hand. Although certainly there's also work that goes on in many groups with much more scaled down devices. In general, in these traps, as I've mentioned, there's an RF potential confinement, and we rely on lasers in our group, other groups with microwaves for coherent manipulation of both the electronic and the motional degrees of freedom. And so you can just picture kind of a harmonic potential in 3 dimensions, which you're able to separate out. It's very deep. With these kind of macroscopic traps, you can think about depths of something like 10 electron volts. With these shallower surface traps, it's going to be not so deep, but still much, much deeper than room temperature. The trapping frequencies are about megahertz. And here's another picture from Rainer Blatt's group, really a beautiful ion crystal of something like 50 ions, probably more. I always forget to count. So what are we looking at specifically here? We're looking at fluorescence of ions in ultra high vacuum, then detected on a camera. You can think of the spacing between these ions here as about 5 microns. And then the gate operations between ions rely on these common motional modes here, also illustrated in a nice picture from Rainer Blatt's group. So with these tools in hand, I want to come back to this diagram that I showed you before. And what I want to highlight for you here is that actually the stages at the top of this ladder of functionality, those are all local network properties. So when we talk about quantum memories or few qubit fault tolerance, that's about something that happens at a single node of a quantum network. And these are things that ions are really good at. Coherence times, actually there's a newer citation here that I should have included. So from, excuse me. So we have now, so there's 10 minute coherence times have been demonstrated with ytterbium. And actually from Ki-Wan Kim's group, more recently, actually an hour has been demonstrated a few months ago in these kind of long coherence times for storing quantum states and ions. Of course, ions are not only good for storing information, but also one can manipulate it with really high fidelity. So that is, you have very low loss in terms of doing coherent manipulation, both of single ions, where you're talking about parts in a million, or doing gate operations between multiple ions. And then it's kind of in the framework of parts in 1,000. And so this really provides a very reasonable, very promising, ambitious, but sort of feasible roadmap towards fault-tolerant quantum computing. Here's a really nice paper that outlines such a roadmap in detail. And then, of course, I want to highlight that there's a handful of companies, both well-established and also younger companies that have been started up to address, actually, in particular, ion trap quantum computing. So ion trap quantum computing, looking good. That's these things at the top of the network table. And the challenging aspect actually for ions is the properties at the bottom, because these are non-local properties. When we're talking about entanglement generation here, we're not talking about generating entanglement between ions in the same trap. We're talking about, can I generate entanglement between ions in different ion traps? And that's something that has certainly been studied with trapped ions, but I would say it's less advanced than all of the work that's been done on entangling ions locally due to shared motional modes. So the argument that I'm trying to make here is that if we can focus on these lower stages of this hierarchy, then we have waiting for us at the top all of these wonderful tools that many, many researchers have been able to develop over the past decades. So we can take advantage of all of these attributes of ions for quantum memories and quantum computing if we can get to do really quite sophisticated network protocols. So what do we need to do first? Well, I want to kind of give you a summary of what's been done in terms of non-local networks with trapped ions. And it's this has really been pioneered by work in Chris Monroe's group, starting with a 2004 paper in which they first entangled a trapped ion with a single photon. That's the paper from Blinoff and colleagues that I've written here above. That was then followed by using this ion photon entanglement as the basis for ion-ion entanglement. So I'm showing actually an image from their most recent paper from 2015, in which they actually had 3 ions, 2 in one trap, a third in another trap, separated by some meters. And I want to just kind of sketch out for you the concept here of how one can use ion photon entanglement as the basis to entangle 2 remote ions. So we're no longer relying on shared motion of these ions because they're not in the same trap. Here we're relying on the fact that these ions have 2 spontaneous decay channels. So this is again an example with ytterbium from the Monroe group, where they're taking it, I'm showing you kind of a simplified atomic physics diagram. They're taking the electronic state up to an excited state where it has 2 decay channels with orthogonal polarizations. And so this is creating an entangled state between the final state of the ion and the polarization state of a single photon. And in both cases, in module A and module B, the photon from atom 2 and the photon from atom 3 is collected by an objective and coupled into optical fiber. So you have now ion photon entanglement. And then by bringing those photons together onto a beam splitter, you erase information about which photon came from which ion. And now this allows you to essentially, this is then the basis for a projection into an entangled ion-ion state. So the final step is to detect those photons. You have 4 PMTs here, and the right detection of photons will now prepare the ions in an entangled state based on the fact that you don't know which ion made which polarization of photon. So you start with ion photon entanglement. This gets you ion-ion entanglement. And so in the experiment that I just summarized for you, again from the Monroe group, these are really exceptionally high fidelities, both of ion photon entanglement at 92%, leading to ion-ion entanglement fidelity in a 78%. So you should compare these numbers with 50% as a classical bound that you wouldn't be able to go above without the help of quantum mechanics. And something that's really extraordinary here, I think, is that this was the first demonstration in 2015 of remote entanglement that was generated faster than the decoherence rate of the system. So faster than the rate at which the system was losing that entanglement. And so I think that should probably give you a sense that, that's going to be necessary as soon as you want to scale up from your test bed system of 1 or 2 or 3. If you really think that you can make this bigger, you have to be able to, build things faster than they fall apart. And that really was first shown here. It's since also been demonstrated with nitrogen vacancy centers in Ronald Hansen's group in Delft. So also to give you another perspective on the state of the art now, 5 years later, there have been really nice, beautiful recent demonstrations with strontium ions in David Lucas's group in Oxford, which have now pushed these fidelities further and also pushed up the entanglement rates. So the picture that I wanted to give you at this point is that there's been a couple of groups that have been able so far to demonstrate remote entanglement on the scale of a couple of meters between ions with remarkably high fidelities. These are in both cases are based on spontaneous emission. And so I want to keep this concept in mind, but now ask you whether we can now construct an ion photon interface based on coherent processes rather than on spontaneous emission. And this brings me now to the third part of my talk.
Just a quick question on the basics. So when you say that this entanglement occurs via spontaneous emission, that's a sort of entangled state preparation via dissipation. I'm not so familiar how this is done and if I'm asking something that is a routine. But if you go back a couple of slides, right, you are saying that essentially here, thank you, that essentially you are generating entanglement via the ions, essentially using a process which is totally non-unitary. It's a process that should destroy coherence, right? The spontaneous decay would destroy the coherence.
Except that you have a phase, from your Clebsch-Gordon coefficients, you have an established phase relationships between those decay channels. So that's, yeah, right. So you're completely right in that you can't run this backwards to put it back together because you don't have access to those particular modes, right? But what you do know from atomic physics is that that there's a fixed phase relationship. So and that's what saves us here. That's what gives us the coherence.
So just to make me appreciate, is the spontaneous decay of the atom you are talking about, of the ion you are talking about here, right?
Yes. And
how this is entangling? I mean, sorry so much. I'm a little bit, I mean, I do theory for trapped ions, but I'm not in the lab of trapped ions. This can make a huge difference, right? So.
So I guess I think the way that I picture it is that when you think about, say, the different decay channels here, and so each of these different decay channels, so there's 2 that are shown, but there's actually 3, right? And they each have different weights, which are given by the Clebsch-Gordon coefficients, but those can also be positive or negative. And that's giving a phase relationship between those channels. And so if there was actually an equal probability to decay in both ways, and you have no other way of finding out which happened, then yeah, this is essentially where it comes from.
I see. No, this helps. Thanks. This helps.
This is a case of ion photon or entanglement that's based on sort of 2 parallel channels. And maybe I'll just briefly mention that you can also entangle ions remotely based on a single decay channel where it's either it spontaneously decayed or it didn't. And in those kind of entanglement experiments, you need a fixed interferometrically stabilized path between the ions, but you can also do it with a single decay channel. Yeah, so thanks a lot for the question, because I think it's definitely not obvious.
No, it wasn't immediate. Let's put it in this way. It was not immediate. Thanks.
So yeah, so maybe it's actually, you know, this is how people started with these experiments, but in some sense, maybe it might be easier from a quantum mechanics point of view to understand how it could work in a unitary process, which is what I'm going to describe now. And so here what we're doing is we're going to couple these ions to an optical cavity. And so this is a picture from the lab. And so what you hopefully recognize right away in the middle is the kind of ion trap that I showed you earlier. It's just tilted by 90 degrees, but hopefully the ion trap is clear. And then what you might not recognize right away would be the optical cavity. So there's two mirrors here and they're facing one another. And so you can think of a standing wave between those mirrors. Even though we're not injecting light into the cavity, we're simply relying in a lot of these experiments on the vacuum field. And so, yeah, this model, actually, so this is a paper, as Arne mentioned, actually from my PhD advisor, Jeff Kimball, proposing some time ago that this kind of idea of an atom or an ion coupled to an optical cavity could be used to link together remote systems. So we're going to start with one cavity. And here's the idea that you should think about the ion localized at the maximum of one of these standing waves of the cavity mode. And then the question is, well, what exactly is the interaction between the ion and this light field? How should I picture that? So this is kind of the simplest possible energy diagram I can show you. And we're switching now to calcium ions. The example I showed you from the Monroe group was with ytterbium. So with these calcium ions, you can picture a ground state on the left. On the right-hand side, you could also think of it as a ground state, but it's actually a metastable state, a D state with a lifetime of about a second. And then you have an excited state here in the middle. And so what I've sketched out for you is a Raman process that will coherently link together the two lower levels, but it's not a Raman process with two lasers. It's a Raman process with only one laser, where the vacuum field of the cavity replaces what you would normally think of as a process with a second laser. So we have a vacuum field, we have the laser, and the point is that these need to have a fixed frequency difference that matches the frequency difference of the two ground states of the atom. And when we can satisfy that, and when we also can sort of satisfy a phase relationship between those two fields, then we can transfer the ion from the left-hand side to the right-hand side without populating the exciting state. So here's a little cartoon version of that working. And we generate in the process a single photon in the cavity from the vacuum. So the ion went from the left state to the right state. A photon came out of the vacuum to make up the energy difference. And of course, the unitary process is that then we would reabsorb that photon, go back to the left, and we would bounce back and forth from left to right and left to right forever. But in the meantime, of course, there's also decay processes. In particular, the mirrors have some transmission. And so the photon can leave the cavity at some time, and that's the ideal case. Also, there's various other channels for spontaneous emission, but the decay channel that we want to focus on is the photon leaving the cavity and then going on to talk to other network nodes.
So, sorry for interrupting.
No problem.
But I'm just trying to think what properties the cavity should have. Should it be a bad cavity because you want the light out, or should it be a good cavity to have like a good coupling of the ion to it?
So that's a really good question because it's this tricky balancing act where I think ideally for network applications, you want something where the fastest rate would be kappa, the cavity decay rate, because you would like to get those photons out quickly to do interesting things with them. And then the next biggest rate would be the coherent coupling between the ion and the cavity. And then the slowest rate would be spontaneous emission. Yeah, that would be ideal. Yeah, in this situation, what usually happens is that the spontaneous emission rate is higher than you want it to be, but there are other good reasons why you chose to use that atom. So in particular here, we really like this wavelength of 850 nanometers in the infrared. So yeah, the other point I wanted to make here, so what I showed you is we have a Raman process, we make a photon, and we can also manipulate the ion. So we can tell which state the ion is in using fluorescence measurements, so we can introduce another laser that couples to a different excited state, and that will lead to fluorescence if the ion is over in the S state on the left-hand side, but it will not lead to fluorescence if we're on the right-hand side. So that's how we're telling the difference between these two. And we can coherently manipulate the state of the ion directly with a laser that couples to this quadrupole transition. So it's dipole forbidden, but the S to D transition is actually the basis for the qubit state in calcium-40. So these are the two states that are commonly used for quantum information processing. So we have a narrow line with laser that can address that transition very nicely and carry out high fidelity operations there. So this is kind of a toolbox for us. And what I've shown you now is that we can make single photons in this process. So we have a nice single photon source because the ion will stay over on the right-hand side until it decays, which will take a second. And so how do we go from a single photon source to entangling the ion in the photon? This is what I want to show you on this slide. And it basically means that we're going to run two of those processes in parallel. So this is the process that I've already showed you, generating a single photon via a single Raman process. And now I'm going to essentially double it by introducing another state on the right-hand side. The reason I can do that is because we actually have 6 different Zeeman states in the D5 halves manifold. So we apply some small magnetic field to split out those states by a couple of megahertz. So we pick out 2 different states from the 6, and we pick out 2 states that will decay with, or not decay also, but here it's a coherent process, 2 states that couple to the cavity with orthogonal polarizations. And so we drive 2 different Raman processes that couple us from S to D. And the important thing here is that then we need a phase relationship between the 2 frequencies on the left. The reason we need 2 frequencies on the left is to match the frequency difference between the 2 states on the right, because the cavity stays at a fixed frequency. That's what I'm indicating with the red arrows. So we describe this as a bichromatic Raman field. And so what we end up with, if we call the photons horizontally and vertically polarized, is that on one version maps the S state to the state D with a horizontal photon. Another version maps S to D prime with a vertical photon. And if we do this in parallel, we have, again, a definite phase relationship between the 2 processes that's set by the phase relationship between the 2 driving fields. And so we can balance the 2 processes in such a way that they're equally probable. The phase relationship is fixed, and so we have maximal entanglement here. And we verify that by mapping out the joint density matrix for the ion and the photon. So we do measurements of the ion in 3 different bases. We do measurements of the photon in 3 different bases. This is an example of the kind of density matrix that you can measure. And you can find that you can generate this ion photon fidelity, the overlap with the maximally entangled state, that's very, very close to 1. And so something that's really nice about doing it with a coherent process is that you're no longer limited by the properties of your spontaneous decay for a particular atom. So you can do things like play with the phase of the state that you generate by adjusting the relative phase of your 2 lasers. And you can also play with the amplitude of the entanglement of the components of your entangled state by adjusting the relative amplitudes of your lasers. So you have more control over this process, which is what we were also able to show at the time by varying the phase and showing that we still created a very high fidelity entangled state. So broadly speaking, I want to highlight that the advantages for quantum networks here are this tunable amplitude and phase. You can tune, when you have your ion in a cavity, you have the ability to tune the temporal wave packet that's of the photon that's exiting your cavity, again, by adjusting the amplitude and the frequency of the driving laser field. And so you have the possibility to generate photons with near unit efficiency in an optical cavity. And then, of course, we can have interesting conversations about what near unit efficiency means, because this is all going to come down to the quality of your mirrors and how lossy they are. But we tend to generate photons in our cavity with a probability of about 80 to 90%. And then we have additional losses in the mirrors when they leave the cavity. Yep. And I want to tell you that then we can go on and use these ion photon entanglement steps as the basis for entangling 2 ions. So we had originally 1 cavity And so we simply put two ions in the same cavity. Back in 2013, we entangled each ion with a photon. And then we showed that we could measure those two photons in order to prepare the ions themselves in an entangled state. And that was something you can bound. You can put a lower bound on the fidelity with what's known as parity oscillations. That is, you can measure, you can manipulate the ions with two pulses. You can vary the phase relationship between those rotations. And then the question of whether your ions are bright or dark as a function of that phase, that allows you, so the amplitude of those oscillations that you see in this question of, in this parity, allows you to put a lower bound on the fidelity. So that's how you can establish that the ions are highly entangled. So I've shown you a story about what we can do with ions in a cavity, or ions in one cavity. And I've told you about 1 and 2 ions and how to entangle them. And so now I want to come to linking together distant ions. So all the work that I've—
question, can I? So about the scheme that you just described. So if I am completely ignorant about trapped ions and I instead come from cavity QED,
yeah,
and think about having atoms inside a cavity talking with the cavity mode, with the photon mode, this discussion and the scheme that you introduced seems not to be specific of trapped ion implementations. Can I do it with cavity QED? Because also there I can drive transitions with Raman beam, with multiple frequencies and amplitudes. I don't have ions. I would have, I don't know, cold atoms that are trapped inside the cavity. And I can think, I mean, maybe I lost some critical aspects, or maybe really the key point is that the typical order of magnitudes that you have in trapped ions will give you better fidelity than I can get in cavity QED. I'm sure it's certainly the answer, but besides an important quantitative difference, is there anything on the mechanism which I cannot do in a cavity QED? I can, right?
No, exactly. It's completely, you can translate it completely to trapped atoms and to neutral atoms. So there's been nothing ion specific here. And it's gonna actually be a trade-off, because with trapped ions, actually, with neutral atoms, you will be able to get stronger coupling strengths.
Exactly.
Which is an advantage. When compared to what people have demonstrated so far with ions. The advantage with the ions will be about coherent manipulation, in particular of addressed coherent manipulation if you're working with multiple ions. And if you want to take advantage of entangling operations between multiple ions in the same cavity. But it's a trade-off. It's not, so yeah.
Thank you.
And the storage times of the ions. So what's very nice about these doing the experiments here with ions, is that you can take an ion and position it exactly where you want it with respect to the optical cavity, and then it stays there all day. So you take all of your experiments with one and the same ion. And if instead you're doing experiments with neutral atoms, those are, maybe in kind of, say in like Gerhard Rempe's group in Munich, we're talking about kind of minutes of storage times. So those have gotten a lot better in the past decade, but still you're taking data with many atoms. And so you have to consider, how do I make sure that each atom is in the same place with respect to the optical cavity?
I see. Thank you.
May I also ask a small question? How can you keep the fidelity high over long distances?
For remote ions?
Yes.
Yes. So I guess what would you think of as the thing that would concern you where you would lose the fidelity?
Yeah, I mean, how you can make this entanglement, I mean, how you can synchronize the lasers or so.
Okay, yeah, now I see. So maybe that actually applies very much to my next part.
Sorry about that.
No problem. So everything that I've shown you so far is in this building, and that you can see in the picture at the University of Innsbruck. And I'm sitting here right now on the 4th floor, but on the side of the building that you can't see in the picture. And here's another building, which I can see out my window. It's about 400 meters away, and it's another cavity in that building. And this has been built up by my colleague, Ben Lanyon, over the past years as part of a new research team that he has over there. So it's also very shiny because it's coated in gold, but it has a very similar geometry to the cavity that we work with. And so it's been really exciting because now that we have these two systems, we can be serious about connecting them to each other. And so, yeah, so this is the vision. We have luckily an optical fiber running between these two buildings at the university and the Institute for Quantum Optics and Quantum Information. And so we want to try to now entangle these systems with each other. So what would we do? The idea would be exactly the same concept that I showed you before, where you have each an ion in each trap entangled with a photon, and you send those photons to some intermediate beam splitter, and you measure the photons, and then you entangle the ions. And that measurement of the photons entangles the ions. And we haven't done that yet, so I don't want you to hold your breath for that report here. So we hope we can have some measurements in that direction very soon. But what we've been working on first is to verify that the photons are in fact indistinguishable, because we need indistinguishable photons for this protocol to work. And so, as you may know, in quantum optics, you know, that the standard approach to verifying that photons are indistinguishable is to rely on the so-called Hung-Mandel effect to have those photons impinge on opposite ports of a beam splitter. And if the photons are really indistinguishable, they should leave the beam splitter at the same port. And so what I want to show you is recent measurements of this Hung-Mandel effect, confirming that we have indistinguishable photons. First, I'm going to show you a measurement that was only done in the experiment on the right-hand side with Ben Lanyon's team. And so how can you do Hung-Mandel experiments with a single experiment? These are about 2 photons generated sequentially from the ion. So the ion makes one photon, and then the ion makes another photon, and you delay the first photon around a loop of fiber so that it can approach the beam splitter at the same time as the second photon. And you might wonder, why do we need to compare photons if they came out of the same ion? Don't ions, you know, always generate photons that look alike? That would be the case if we didn't have a cavity, but you can wonder, you know, actually the cavity is going to do some interesting things to the photons. So it's actually no longer obvious, or it's no longer the case that they're going to be entirely distinguishable. Due to spontaneous emission, which is supposed to be suppressed during the Raman process, but there's always some chance for spontaneous emission. So here's a plot of examining kind of from our collaborators at Nicolas Sanguard's group, who was formerly in Basel, now is in Paris, examining these kind of photon probabilities, understanding the role of spontaneous emission here. And so the point being that the photons that come out of this system are not transform limited. There's some role that spontaneous emission plays. Nevertheless, we can see a very good signatures of indistinguishability in this so-called Hung-Mandel dip. So here's on the top, what you see is a model from the Sanguard group, a theory model of what the photon temporal wave packet should look like. And on the bottom, what you see is, or first, that it agrees very nicely just what the photons by themselves look like. And then that allows us to compare theory and experiment for these Hung-Mandel experiments where the photons impinge on the beam splitter. So the green is where the photons have an artificial time delay has been introduced so that they shouldn't be indistinguishable. And therefore it is possible for photons to exit the beam splitter at opposite ports. But in the blue case, when the photons arrive at the same time, we see that there's this characteristic dip, and that establishes that the photons are indistinguishable, that they don't arrive at opposite ports. So we can examine this first for a single cavity, which is what's been done here. And then in more recent experiments, we've looked at this for our 2 different systems. So photons from here at the university, photons from the Ikoki building. And here's a picture of a similar measurement results. So the red is when there's been an artificial time delay introduced. But when we have coincident photons arriving at this intermediate beam splitter, we see that we don't have photons exiting opposite ports. So we see that we can have a nice verification of this indistinguishability. This is also more information about the agreement with theory here that shows us that we can play with the coincidence window in order to boost the visibility of the system. What I want to emphasize is that we've observed this Hung-Mandel interference, and we're working very closely together with our collaborators in Nicolas Sanguard's group to understand what this means for the right parameters to choose for remote ion-ion entanglement measurements. So with that, I want to point out how we'd like to go beyond 2 network nodes. So this is just now kind of stepping back and being a bit more general. Pretty much, I've shown you about our work connecting 2 nodes, but what you should know is that this is also basically the state of the art. People with different systems, neutral atoms, NV centers, building nodes between, say, up to 1 kilometer in distance. But everyone would like to go from kind of 2 to 3 to many. So I've tried to argue that cavities are a particularly nice interface with which to do it, although they do introduce additional complexity. And I've shown you a system that's not particularly scalable, right? That somebody builds in the lab over many months or even years to get an experiment up and running. Certainly in the field, there's a need for moving to more integrated and scalable devices. Other kind of key issues that we need to solve more broadly in the field include how do we interface with other matter-based qubits via frequency conversion? How do we take advantage of the fact that we can have multiple ions in a single trap? And in particular, how can we use that for error correction? Because we know that these steps are never perfect. And how can we use that to protect information locally? And finally, something that we're very interested in is implementing proof of principle network protocols in these small systems. So at a small scale, going from 2 to 3, I just want to show you a picture of our second cavity experiment here in my group. So I've shown you my working experiment up on the left-hand side, and we also have a fiber-based cavity here. So we've gone through a handful of iterations, as some of the people in Fair-Dimensional College group know. We've been working on these fiber cavities for several years, and this is actually the 3rd generation of this setup. In our current setup, we've trapped ions for the first time last year. What you see here is kind of a schematic, essentially the thing that's kind of, so there's a picture, but it's hard to see from the photograph what's really involved. And so in the lower left-hand side, you see more of a diagram of the system. And so this is actually also a linear Paul trap, the thing in gold. It's kind of like a slice through the one above, but it's also trapping ions along the axis that goes from the left-hand side to the right-hand side. And then what you see kind of coming from the left and the right are optical fibers, and there are little mirrors on the ends of those fibers. So this is how we're coupling ions to these little fiber mirrors, or to the cavity that's formed from the fiber mirrors. We have some preliminary data on that ion cavity coupling, but right now what we've been working on is both on understanding the role of dielectrics in these ion trap heating rates, and also on the stabilization of unlocking the cavity. So so kind of a lot of technical challenges in this system. We're optimistic about it, but we're not yet able to carry out the kind of ion photon coupling experiments that we are in the other system. We also are working on kind of more ambitious designs based on microelectromechanical systems that are being developed by a group, by Dan Cho's group and Taeyoon Kim, also Minju Lee in Seoul. So with that, I think maybe I will just briefly mention the last part of my talk so that there's also some time at the end. What I want to tell you here very generally is that we can use these systems that I've told you about, ion traps, cavities, not only to explore, the quantum mechanical world of atoms, but of course we know that quantum mechanics also describes the macroscopic objects around us. So we can ask, what would be ways that we can observe superposition and entanglement and live and dead cats at large scales? And would there be ways then to do interesting things with such states? So in particular, what I want to think about here is the motion of levitated systems, like a particle here would be like a silica particle, a little glass bead, say about 100 nanometers in diameter, and we can suspend it. So people have suspended these, of course, in optical traps or magnetic traps, but for us, we're focusing on ion traps, and that we are very familiar with already. So what role then do quantum interfaces play for the motion of these kind of particles, and how you could prepare them in a quantum state? The idea is that if we can get light to interact with the motion of these particles, it would allow us to, it gives us the ability to tune the particle to control it in a quantum mechanical way. And so there's been a handful of these kind of optomechanical experiments which are just now reaching the quantum regime for these levitated systems. So this is a picture from an experiment in Lucas Novotny's group at ETH, which has just recently brought one of these levitated nanoparticles to the ground state or to very near the ground state of motion. And also Marcus Aspelmeyer's group in Vienna has now brought one of these particles to the ground state of motion. So it's kind of a pioneering time for these little nanoparticle experiments, but it's very clear that the strength of the interaction between light and motion with these particles is pretty limited. So here's where the ions come in. What we're working on as a long-term vision is to introduce a third interface here, a second interface, a third system to an ions electronic state as a route to generating quantum states of motion. So this is a proposal that comes out of Ignacio Sirac's group together with Oriol Romero Izart when he was a postdoc there. And the idea is that we're trying to couple both an ion and a nanoparticle to an optical cavity, that is to the light field in an optical cavity, in order, again, in the long term to explore the quantum mechanical states of motion of the particle. So we're certainly not in the quantum regime yet in my group. Just to sort of summarize the results that we've done in the past couple of years, we've looked at loading and cooling these nanoparticles in an ion trap, so we're able to prepare them in ultra high vacuum. We're able to cool them down using a handful of different techniques to temperatures of something like 10 millikelvin. Still, these are kind of 10,000 quanta, so there's we're not anywhere again near kind of 1 or 2 quanta, but there's sort of definite routes to get there. We are testing ways to prepare ions and particles in the same ion trap. We're working on integrating our system with an optical cavity, and broadly speaking, we're hoping that the tools that we develop can be applicable to the quantum optomechanics community. So that was just kind of a side comment on other or perspective into this work that we're doing in quantum optomechanics. But I want to come back then to the question that I started with about future quantum networks based on trapped ions. So I argue that there are really a broad range of exciting applications for quantum networks, and that ions are particularly well suited to be placed at nodes of these networks. So I highlighted our recent demonstration of Hongo-Mandel interference, also first between ions from the same node, photons from a single ion in a cavity, but more recently, unpublished work with cavity-coupled remote ions. So that puts us nicely on the way to remote ion-ion entanglement. And finally, I showed you that these cavities can also provide an interface to the motion of macroscopic objects. Certainly in the long term, there may also be interesting connections here with quantum networks in terms of interfaces between hybrid quantum systems. So thank you very much. Let me also show you a picture of the many students and postdocs who have really contributed and worked very hard on these projects. Thank you.
Oh, thanks a lot for this super interesting talk and pretty broad talk. What Tracy mentioned actually at the end, this cavity quantum optomechanics, if you want, just to shamelessly use this as an advertisement. We have her collaborator, James Millen, who I also co-worked with in London. He is giving a talk about this on the 26th of November. So thanks a lot for the nice talk. I'm sure there are questions. You can ask your questions in the chat. Just unmute yourself, ask them like this. So yeah, thanks. Sure, there are questions. If there are no questions, I start with a question.
Yeah, I mean,
oh, there was a question.
I have a question. I mean, I hope, okay, I guess I'm not jumping in front of anyone. Okay, fine. So, well, my question would be kind of two questions, and that has to do with sort of, if you could imagine combining these ion traps with let's say the cavity the circuit QED systems. So, and what I mean is twofold. Now, one, I know that, for example, in circuit QED, like you could imagine, you know, sending a pulse like a microwave tone, and then depending on what the state is of the like depending on the parity of the qubits inside, you could like the transmission and reflection of the tone could be different. So I was wondering if that could be possible to be done in these ion traps with cavities. So for example, if you send a light tone into the cavity and let's say the resonance of the cavity would be influenced by the, well, by the state of the ion. So that's one thing. And the other thing is that, well, if you think about, let's say this transmon qubits frequencies, you would get like a few gigahertz, I guess, right? So, but then, for example, the qubit frequencies in like David Lucas's group in calcium-43 would also be something like that. So did you think about like combining, you know, making an interface because the frequency is the same, making an interface between, you know, the transmons and the ions, and if that could be helpful? Thanks.
Yeah, thanks. Those are two great questions. So I think the first question was not about specifically linking them, but more about adapting the methods that have been used. And the second, I think, was about a link. So concerning the methods of reflecting or sending these pulses to the cavities, yes, so that's definitely been explored with neutral atoms in cavities. Again, kind of going back to proposals from Jeff Kimball and Lu-Min Duan, that you could do gate operations by reflecting either photons, or also you can reflect coherent states off of a cavity, and then kind of either the light goes in or it doesn't based on the state of the atom in the cavity. So that's work that's been done with neutral atoms. Similarly to the question from earlier, that there's no reason that doesn't apply also to ions, except that those experiments, like the superconducting qubit ones, really rely on a very strong, or a strong coupling rate with respect to dissipation rates. So their ions are going to be more challenged because dissipation rates are playing a more significant role than with neutral atoms. But you could certainly apply those techniques also with ions. There's no reason that fundamentally why they don't apply. In terms of the second question about an interface, I think the primary concern would be about bringing anything near to an ion trap, in particular dielectrics, or any kind of introducing other materials, and what that means for then the trap, the integrity of the trap. So the frequency, but in particular whether you start to heat up the ions in your trap. Yeah, I think that would be practically the primary concern.
So I did have my chat box closed, so I didn't see that there was quite some activity, especially Alexei writing to me whether it's okay to ask questions. I think it's okay to ask questions, but I also like the way that Ferdinand is doing it now by raising your hand, and maybe it's a bit more orderly than I can can ask Ferdinand now to ask his question. Maybe that's a good way to.
Yeah, thank you for the great talk. My question is about long distance entanglement, and if you want to use this way that you described to network between different processors of the quantum computer. The timescales are pretty slow, aren't they? So you make a point that they are much faster in between time, but that doesn't help us so much if we want to make a real computer.
Ferdinand, your microphone seems to be very bad.
Oh, sorry.
It was very quiet.
Now?
Oh, much, like an order of magnitude better.
Oh, sorry. So I wanted to ask about the timescales of the gate operations if you are networking between different nodes of a future quantum computer. Of course, we need to scale things up, and if you think of units of 50 ions doing their job and then interconnecting them with optical links, if we have a rate that is so slow as it is, then it exceeds the single ion decoherence rate, but doesn't necessarily exceed the 50 ion decoherence rate. And especially it is not fast enough for doing meaningful entanglement sharing between the two nodes. So how can you speed these things up? I think the small cavities are one option, but is it really sufficient? That's my question.
Yeah, I don't know the short answer. I mean, I think this is an important point. Let me go back actually to this picture, this kind of image here from Chris's group. Oops. Yeah. So yeah, I think, as you say, so with current setups, we're talking about kind of maybe you can get a kilohertz in terms of the rate at which you're generating remote entanglement. And so that's a beautiful fundamental demonstration, but in terms of having it be practically applicable, that has to get faster. The fiber cavities are certainly for us, a promising route, but it's not clear how much we can win simply with fiber cavities. I would imagine that it's a combination of these miniaturized cavities for a faster coupling rate, like with the fibers, but also that you're doing something like you see in this diagram in the upper left here, where you're then taking advantage of multiple ions and also different species. So you could imagine that, you have some species, in this picture, it's barium, that where your only task is to generate lots of entanglement as fast as possible. And so they're kind of rotating these ions around and then mapping that onto memory qubits. So sort of in parallel with your computing work, you have this kind of memory of a lot of other qubits where you're just trying to hold on to entanglement as a resource. That's the concept, but yeah, can we get it to work? I think, yeah, it's what we think. We only know that when we try and figure and see the interesting ways in which it doesn't work.
Thank you very much.
There are more questions. Again, you can also raise your hand and then I can ask you to unmute, or any other mechanism to discuss a bit. Well, I was interested in, well, you have demonstrated now this Hongu-Mandel effect with two different photons, if you want, or photons originating from two different setups. What is the direct next technical steps towards, what would you do? I mean, direct these photons to manipulate the ion in the respective other experiment, or what would you do? Yeah,
you mean now essentially following the Hongu-Mandel, right? Yeah, so I'm also grateful for the question, because it comes back to the question that was asked earlier, which I didn't completely answer, the one about about long distances and about stabilization. So what we've done, what we've focused on kind of in the past year or so is both, electronic timing stabilization, which, sounds straightforward, but it still requires a lot of work. So it requires, we're both of the two experiments are synchronized to local GPS. And then more challenging is the frequency stabilization of the two cavities. So there we make a beat note between the lasers that are driving the Raman process, and that stabilizes us locally. So that gives us the frequency relationship there. So I think that we have everything in place right now to try to generate the remote entanglement, and that we are kind of sorting out here in my group, trying to sort out why our current ion photon fidelities aren't as high as we expect. Then I guess the final step before trying to measure ion-ion entanglement will be that we have a method in place for correcting polarization drifts that happen in the channel, but we need to test that a little bit more, or we need to test it with the single photons. Yeah, and then the final comment would be, because the original question had been about sort of things getting worse as you get longer away. So the issues that I point out, like with stabilization, I think that doesn't particularly matter how far, how many hundreds of meters the buildings are apart from each other. The first problem you run into, I think, is the wavelength at 854 nanometers. And so that's good for kind of kilometer scale stuff, but not tens of kilometers, at which point you really need frequency conversion. Ben's team over at Ikoki has had some beautiful results converting these entangled photons to telecom. So that would also be sort of in the near term where we'd like to go as well, converting photons from the 2 locations up to telecom, which would let you cover much longer distances.
Well, thanks. Is it fair to say that I don't know, everything Ramir also mentioned it, like the work by Rempe et al. I mean, they do have already 2 cavities with neutral ions, and they're doing all kinds of protocols. And now you do it with ions, therefore you have to basically take a hit on the cavities because you cannot get as close as you want and so on. But you do have much better control about the ions, if you want, compared to the neutral atoms, right? Is that fair to say? I mean, you basically, it's a pretty straightforward experimental protocol because the papers have already been written. It's for neutral atoms.
Yes, I think that's a fair description. Again, yeah, I think that the where you get the strengths of the ions, I mean, for the current experiments are that you can really pin down the ion photon and characterize the ion photon coupling to the cavity. But and also, okay, yeah, I mean, but they can do, so yeah, I mean, neutral atoms can also do ground state cooling in 3 dimensions. I think the sort of cooling is a bit easier, but it's all, you know, everybody can do these things now. Certainly, I think the real advantage for the ions will come later on when you can harness kind of store, you know, logical qubits entangled across multiple ions.
Thanks.
So,
I think there are 2 more questions. Ramir, yeah, maybe you before Ferdinand. Then.
Yeah, right. No, but I lost connectivity. So this is maybe a little bit wild. So I asked the question in 2 ways, and you decide to which one you want to answer. Okay. So I come again a little bit from this cavity QED business, and as you probably know, there you can engineer entanglement with dark photons, with dark states. So you can create entanglement even if the cavity is very lossy. And basically you can generate entanglement via dissipation. And this is great because normally you entangle with something that is your adversary. So makes any sense in your internet network to have cavities where you entangle a lot of ions, maybe in a way robust to dissipation. And to create
I think we lost you at the important point of your question.
Say that again?
There was an internet hiccup.
Yeah,
basically.
I know. Today it's better. This is not great because I'm the chair of the next seminar. So I try to start again in simple words. Can you entangle several ions in one cavity, several ions in another cavity, maybe in a way that is robust to dissipation with dark states, and then create many body entanglement, long distance entanglement via sending photons? Because you describe a situation in which you have one ion entangling from another ion of far distance. But for instance, in cavity QED, people know very well how to get entanglement between atoms in a cavity in a way that is robust to dissipation. And so if you have to worry about dissipation only when you communicate between distant cavities, maybe you can get a considerable advantage. Was I too wild? Or did I clarify my point? I mean,
so I think I understand. And then I think what becomes particularly important is knowing what kind of dissipation, because for a lot of these cavity QED protocols,
cavity losses.
Yes, right. So if your only dissipation is cavity losses, I mean, I wish our only dissipation were cavity losses.
No, right. But this was a little bit dumb from my side, right? Because you have all the time the excitation of the atoms of phase noise dephasing. This is of course very bad for entangling. You cannot do the same trick, of course.
So that, yeah, I think we try to play a lot of games where we can squash down the role of spontaneous emission, because we would love to be in a regime where all we had to worry about was coherent coupling and dissipation via the cavity. That would be ideal.
No, sure, of course. You have other level of problems. No, sorry, this was partially obvious.
Okay, thanks. Ferdinand had another question. Or at least he's raising his hand.
Yes, I have another question. Hopefully I can, you understand me now better? Yeah, okay.
Perfect.
So my question is about you are fixing the phases with this cavities, you are also restricting yourself to one or at most two ions in the cavity, but you could measure basically the correlations of emitted photons also without cavities in free space. And then you could even project the whole state by the right click into a Dicke state or so, or whatever, and generate maybe more. It's a little bit like Yamir was going into this direction to extend it to larger crystals or so. Is that possible? Do you think about this also?
So I'm not sure, are you thinking about larger crystals in the same cavity or in free space? Because you also mentioned free space.
Well, in free space, you have all the phases that you have to adjust because of the travel of different phases that come due to the different travel of the photons up to the detector. So it may be a little bit more variable. You can adjust more in the state, but also it is a more complicated situation. So maybe the cavity is easier, I think, yeah.
Yeah, so I think that there are a lot of routes. Yeah, I think starting with one or two ions is about, you know, keeping things simple until you understand what's going on. There's some nice proposals. For example, there's a 2011-13 paper by Lukas Lamata and colleagues, including Misha Lukin and Vladan Vuletic, proposing an ion cavity transducer. So kind of using really a chain of ions coupled to the cavity and harnessing that collective coupling, but still taking advantage of addressing. So kind of mapping single ion encodings onto the collective encoding. And I think that would be also one nice route for us with the fiber cavities, or with our current fiber cavity geometry, is it would allow, or that will allow us to trap ions along the cavity axis, which then is a route to putting in more than, you know, 3 or 4 or 5. So with our current kind of orthogonal geometry of the ion trap and cavity axis perpendicular, you're only going to get maybe 5 or something ions. But if you can align those two axes, that would also be a route to what you're describing.
All right, are there more questions? Well, we have another 3 minutes, so might as well ask. Ferdinand, are you raising your hand again? Is that what happens here, or did you just not lower it?
No, my hand was still up. I have no more question. Just to say thank you, Tracy. Thank you very much.
Oh, you're welcome.
All right.
Yeah, this was a great talk. Thank you so much. I learned a lot. Great,
then let me, just before you all leave, let me advertise the next seminar, which is going to be given by Anastasia Borszewski from Groningen, and it is going to be more, a bit more in our field of work, atoms and molecules as probes for physics beyond the standard model. So quantum, standard model extensions. So it's a broad range. So, okay, let's bring this to an end. Tracy, thanks again for coming. It was a spectacular talk. It was great to have you.
You're welcome. Thank you so much for the invitation, and have a great afternoon.
Thank you very much.